Okay, so what we just said is that so this is another algorithm to compute the minimal spanning tree. Okay, we didn't go to all the implementation detail of the cross-cause algorithm. Okay, to implement it efficiently, you need a unified data structure. But I hope the high-level idea, this very simple greedy algorithm, is clear. Okay, you simply sort all the edges and add edges one by one. Throw away any edge that caused a cycle. That's it. Okay, so since you sort the edge from small to large weight, you keep adding the cheap edges. You basically try to grow, connect your new nodes with the cheapest possible total weight. That's the idea. Okay. Okay, so we're not talking about the correctness of a cross-cause algorithm. Okay, I hope the intuition is clear that this greedy algorithm always try to reach new nodes using through the cheapest edge. Okay. All right. Now I want to say a few words about this minimal relation between the minimal spanning tree and the so-called hierarchical clustering. Okay, or the clustering that started with clustering. Now, at the beginning of this class, remember that we look at the so-called clustering problem. Okay, which essentially that you're given data. Let's say you're given n points in a d-dimensional space. Let's say each point represents the record of some person, like represented the age. Let's say as a student, represent the age of student's ID, different dimension, different measurement. Okay. And the goal of clustering is to identify the groups in data, basically the so-called cluster. Okay. So for example, if I give you this point set, then it's kind of intuitive that here there are two clusters, two groups. Okay. I have one group here and I have another group here. Okay, so visually it's very clear. But then the question, the clustering problem is that how do you find the groups in data using an algorithm? Okay, all right. So now remember that one way to model this cluster problem is that essentially I want to assign each of the node a color, be it red or suppose we want to find two clusters. Then I want to assign each data point a color, say red or blue. Okay, that's a class label, so that you a good cluster, basically you want to make sure that these two groups are separated, right, as much as possible. And this is measured by saying the distance between the closest pair of red and blue points is maximized. Okay, so for example, if I say all of these points here are red and all of these points here are blue, then in this case the separation between these two clusters, the distance between the closest pair of red and blue points would probably be this. Okay, this would be the separated distance, which is pretty large. It's actually maximized. Okay, so this is a good clustering. Okay, but if I say that, okay, everything here are red and everything here are blue, then this is a bad clustering, because in this case, the separation distance would probably go to these 2 points. That's the closest, the red and the blue point. Okay, and it's very small. Okay, so what we want is that given this n points in the RD, I want to give them class labels so that the distance between clusters, between points from different clusters is maximized. That's what we want to do. Okay, so this is a 2 cluster example. Okay, but in general, you may want to find more than 2 clusters as well. Okay, and so this is a bad clustering, and this is a good clustering. Okay, and remember in the first class, how did we solve this? We say, okay, here's a way to solve this optimization problem. I can just enumerate all possible assignment of red and blue to each of the nodes. Okay, and then for each of the assignment, I check this distance between the closest, the red blue points. Okay, and I return the one where this quality is maximized, is the best. Okay, and of course it works, but it's not a good algorithm because the number of possible assignments is 2 to the n, where 2 is the number of clusters you have. In this case, you want to find 2 clusters. Every point has 2 choices, so that's 2 to the n possible assignments, which is huge, highly not inefficient. Okay, and the question is, can we do better? Okay, and it turned out that we can actually convert this to a graph problem. Okay, and in fact, the minimal spanning tree algorithm we just introduced can be used to solve this. Okay, so what do I mean? Well, so we're given this endpoints. Okay, so I'm using this very simple example here. So in general, we're given endpoints in RD. Okay, I'm going to first map this. So this is the input point. So let me just change it to. So this is our input point. Okay, so first I'm going to convert it to what I call a distance graph. What is this graph? This is basically a complete undirected graph on all these nodes. Okay, in other words, you add an edge between any two pair of nodes. Okay, and what's the weight? The weight of each of edge is simply the distance between these 2 points. Okay, so that's it. Okay, so that's what we have. Okay, so let's say that maybe this distance is 1, this distance maybe is 1.9, this is 1, 1.9, and maybe this distance is 2.4, this distance is 1.8, that's it. So this is our graph, okay? So where the weight of an edge is the distance between two endpoints. Okay, so we call this a distance graph. So step 1, I convert the point set to be this graph. Okay, all right. Next, what do I do? Then, let me move this. Okay, next I'm going to, given this distance graph, I'm going to compute a minimal spanning tree on top of that. Okay, so in the previous point set we've seen, okay, let's assume that in fact you don't have to use a Kraskow's algorithm. You can also use Prim's algorithms here. Okay, so let's say for the previous point set, this is the minimal spanning tree of that weighted complete graph. Okay, all right. So we look at this graph intuitively. What is this minimal spanning? So this is the minimal spanning tree. So this is the minimal spanning tree of that complete weighted distance graph we created. Okay. So what's special about this tree? Now, intuitively, remember that what minimal spanning tree is trying to do is that you want to connect all the nodes using as little cost as possible. Okay. In other words, here the weight is distance. In other words, you want to connect all the nodes using, you want to connect the close points first, right? Because you want to keep the connection total cost to be low. So you want to use the short edges. You want to connect first points that are close by, okay? You only use long edges when you have to, okay? And when that happens, you use the cheapest long edge, okay? So in this minimal spanning tree, now what we can do is that, so now I say that I want to find what is the best two cluster of this data set, okay? What do? I basically can just remove this longest edge, okay? And then this would give me two clusters, okay? So when given a tree, if I remove one edge, then I get two components, okay? And if I remove the largest weight edge, intuitively, I say that I'm trying to connect I want to find the two clusters that can be connected using as little cost as possible. This largest edge is basically the cheapest way to connecting this portion. Let me give them color, the red portion and the blue portion. Okay, you can think that to break them, if I cut it this way, this is basically the closest distance between a red point and blue point. I want this length to be as large as possible. Okay, so if I didn't, let's say, if I didn't remove this edge, I want to get two clusters. So I want to remove an edge from the minimal spanning tree. Okay, because removing any edge would give me one extra component, because this is a tree. Removing any edge would disconnect it. Okay, so suppose I didn't remove this edge. Suppose I removed this edge. Okay, if I remove this edge, what do I get? I get this component. Okay, and I get this component. Okay, and intuitively, what is the closest pair of red and blue points? Well, intuitively, it turned out that this is the edge. This edge that I used for minimal spanning tree is the closest, is the cheapest way to connecting them, okay? And that's true intuitively because that, remember, my tree is, if there's a cheaper way to connect this red and the blue, my minimal spanning tree should have used that edge because I'm looking for the cheapest way to connecting all of them, right? So this green edge is indeed the cheapest way to connect this red component and the blue component, okay? And what do I want in my clustering? I want to remove one edge, and so that the cheapest way to connect them back is maximized. Okay, that's why this is not a good choice. A better choice is to remove this edge. So that is the resulting components, the red one and the blue one. The distance between them is largest possible. Okay, so that is the intuition. Okay. Now, this is if I want to get two components, I just remove one edge. If I want to have more than two components, if I want to have three components, then you ask, what is the next edge I should remove so that the separation between all this cluster is largest? Okay, and it turned out that you simply remove the next largest weight edge in the minimal spanning tree. Okay, so in general, if we remove k-1 largest edges, means that the edges with largest weights, okay, that give you k cluster, okay, and turned out that this is the best k cluster where their separation distance is the largest possible. Okay, all right. Now to prove what I just said, to show that this algorithm really maximized the inter-cluster distance, takes some work. Okay, so we're not going to prove it here. Okay, but the intuition is that minimal spanning tree is finding the cheapest way to connecting them. Okay, in my class, what does cluster want to do? Cluster want to connect the points in the group use as cheap as possible. Okay, and the distance between groups should be large. Okay, so that's why that you want to find the minimum smallest cost way to connecting nearby points. Okay, and then when you want to find the grouping between them, you want to remove those edges from minimal spanning with the largest distance, so that this indicates the inter cluster distance. Okay, so this is what we do. Okay, so a very simple clustering algorithm now. You just compute the minimal spanning tree. If your target is to get a k cluster, then you remove the k largest weight edges from minimal spanning tree, k-1, that give you k components. Okay, that's it. Okay. Now this is the what I just said is just a generic way to get to this cluster. Okay. Alternatively, I'm going to give you another intuition to hopefully you see why this minimal spanning tree, in fact, exactly the Hierarchical algorithm works for this clustering purpose. Okay, so I'm going to explain this a bit differently. Okay, oops. Let's see. I think I'm going to actually talk about this shortly in the hierarchical clustering. Okay, so let me just point out that using what we just talked about, the time complexity. So I'm going to come back to this in a minute. So the time complexity of the approach I just described is, remember, it's E times log V. But in this case, since our graph is a complete graph, okay, because we connect all pair of nodes where the weight is their distance. So that means that E equal to V squared in our case. That's why this clustering algorithm takes time, V squared log V. Okay, so because our graph is dense in this case. Okay, all right. So it turned out that this Hierarchical algorithm actually coincide with something called single linkage clustering algorithm. Okay, so I'm going to introduce this when I'm talking about the so-called hierarchical clustering next.